thrilling sequel if you are brave enough to see Mr. Fizziks 2.
Oh, you're here already. Oh well, nice to see you. Just having a cup of coffee, but I don't mind putting it down to talk to you. Now you're probably sitting comfortably waiting to hear all about how light behaves and how it moves through matter and so on like that. Well, bad luck, because I'm going to give you a lecture on electricity. You like that? Rewind. A lecture on electricity.
So many words about electricity that people don't understand. Here are some of them. If you understand these, then you're on the wrong channel. Go to ITV. But if you don't understand them, by the end of this lecture, either you'll be fast asleep or you will understand, well, at least one of them maybe.
To understand properly about electricity, did you notice that I don't like to use the split infinitive? These days I always say to properly understand. Ugh, not very good English. Anyway, to understand properly about electricity, we need to understand the atom, and that means some history. And I want you to have a little guess. When do you think the idea of the atom was first thought up? Have a little guess. If you get it within 50 years, I'll give you 5 brownie points. Have a go. Right, well I bet not many of you got it, but in fact I hope you didn't. It was actually first postulated by Democritus in 400 BC. This is an ancient Greek photograph of Democritus. Now you've all heard of Democritus. Just imagine, he was one of the philosophers. They were all philosophers in those days, weren't they? Imagine when he was little and his mum said, "What do you want to be when you grow up, Democritus?" And he said, "I want to be a philosopher." And she said, "I'm not having you being a philosopher standing around thinking all day. Do something useful like being a stone basin." But thought he did. And he thought of lots of things. For example, we all know, don't we, that democracy is named after him. I think they decided to do that after a vote. And also the Democratic Oath. That's what he uttered when he stubbed his toe on a piece of masonry. But best of all, he said, words to the effect, in ancient Greek, "I think everything is made up of tiny particles. And I'm going to call those particles atomi." And atomi is the ancient Greek meaning indivisible. So good old Democritus. And all the local people went, "Ooh." That was about 400 BC. Now, that stood until along came another philosopher, Aristotle. You've all heard of him. Actually, he looks quite similar, doesn't he? They both have that same sort of pale Greek complexion, don't they? Anyway, this was in about 350 BC, about 50 years later. Because you see, in those days they counted backwards. Funny lot, weren't they, the ancient Greeks? Anyway, Aristotle said words to the effect that, don't be daft, if everything was made of little bits, then it would all fall to pieces. And all the people went, "Ooh." And then Aristotle continued and said something like, "There are only 4 elements, earth, fire, water and air. And not a lot of people know that." We don't know, he might have spoken like that, mightn't he? So the idea of the atom was lost for over 2,000 years. I should add 2 things. One, that's not my hat on the wall, it's just there, I don't know why. But 2, the ancient Greeks also knew about static electricity. It happened when an old chap called Thale, well I don't know if he's old, but he would be by now, was actually cleaning his jewellery, which was made of amber, and he noticed that when he rubbed it, it charged up. I guess it repelled other bits or something like that. lost for about 2,000 years. But in 1808, a scientist called John Dalton, who was British, oi, 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 stop it. Sorry, that's Cranbrook Choral Society. They're practicing in the spare room upstairs, and they're not even social distancing. John Dalton reinvented the idea of the atom, and he called it the atom because of what Democritus has said. So he said, words to the effect that I believe that everything is made of tiny particles, and for every element, because they discovered lots of elements by then, for every element the atom is different, and in that element every single atom is the same, which was pretty good, not quite right, but pretty good. A bit later, so he theorised then that the atom was like a plum pudding, although I prefer to call it a currant bun, currant spelt with an A, where the pudding was positive, and all the plums, or in my case the currants, were negative. And there were as many negatives as there were plus. So overall the atom was neutral. Now a bit later in the 1800s, J.J. Thomson discovered the electron. And the electron was discovered to be a tiny, tiny particle, negatively charged. Now, don't worry about this plus and minus business, because they're just labels. Because they've found there are only two different charges, if you call them plus and minus, that's fine, there's nothing else, rather than A, B, C, because you could go on for 26 times. So the electron is negatively charged, and so they reckon that the plums inside the pudding were these electrons. And it was about then that there was this molecule party, and one molecule was talking to the other, and he suddenly said, "Oh no," he said, "here come the atoms. Don't believe a word they say." And the other one said, "Why ever not?" And he said, "Atoms make up everything." And a bit later, along came Lord Ernest Rutherford, and he was famous for a particular experiment called the alpha scattering experiment. In actual fact, it was done by two people called Geiger and Marsden, who were probably, I don't know, they might have been his students or something like that, but he got the credit for it. And it was all about probing the atom and finding more what it was like. I've got to show you this on a little diagram.
Now, this whole lot has to be in a vacuum. So to start with, we're talking about complicated apparatus. Here we've got a big block of lead with a little hole in it and a piece of radium right in the middle, and radium gives out alpha particles. Now we know that alpha particles, there's the Greek symbol for alpha, alpha particles are positive. They've found that out by seeing which way they're deflected in electric fields. And here was a very, very thin gold film held suspended there. This is a fluorescent screen, and it's zinc sulfide. And what happens is, if something charged hit it, it gives out a little glow. That's what's represented here. But you have to be in total darkness and let your eyes get used to the dark. It's really, really not easy to see. So quite complicated apparatus. And here goes what happens. The alpha particle beam comes along to the gold foil, and most of those go absolutely straight through. So actually there's a bigger concentration here than there is elsewhere. But some were deflected. Some of them through quite large angles. And they thought, that's a bit weird. And apparently they were very surprised by this, but I don't believe that, because you wouldn't go and build all this expensive apparatus just in case you got surprised. Here's what it all means. The gold foil was used, they used gold because you could make it really, really, really thin, gold leaf. Even so, it's still about 2,000 atoms thick. Now imagine that being made of bricks, 2,000 bricks thick. It is most unlikely that an alpha particle can go straight through between the bricks. So therefore, it must be going straight through the bricks. So, if we're thinking about an atom as being like that, it means that most of these particles are going straight through. 2,000 of them, no problem. However, some bounced off. So what would make a positive charge bounce off another positive charge? So supposing there's a positive... Oops, stuck my pen through the paper then. Supposing there's a positive charge there, then anything that came near it would be deflected. And if it came closer, it would be deflected more. And if it came incredibly close, it would come straight back. So that was the conclusion of this experiment, that the atom is mainly empty space, and it has a positively charged something or other at the middle, which is really, really tiny. And that positively charged something at the middle they called the nucleus. So a new model of the atom is a tiny nucleus positively charged at the centre and electrons orbiting round the outside.
So after Rutherford's discovery that we got a nucleus in the middle and electrons going around the outside, they decided that's what the atom was, and that's exactly what it is. And this is the sort of picture that you have in mind and they show on telly and so on when they want to picture the atom. But it's not quite like that. Let's put it in proportion. Supposing the atom, let's scale it down, supposing the atom was the size of the Albert Hall. Well, the nucleus would be a P in the middle. Now, if you had a P in the middle of the Albert Hall, you'd probably get arrested, but that puts it all into scale, doesn't it? That is the relative size of the atom. And of course, some are much bigger than that as well. And what's going around the outside, these electrons, every electron is a 2,000th the weight of just one of the particles in the nucleus. So the electrons are tiny, which means then that the atom is mainly empty space. And everything's made up of atoms, as we know. And if everything's made up of atoms, including us, we are mainly empty space. And I suppose that's more obvious in some people than others. Okay, so how does knowing about atoms get us on to talking about conducting electricity? Okay, first of all, let's have a picture of a really good conductor.
Ah, that's me. That was in 1970. I'd just finished being a student and was just about to start my first ever job. I did that for the whole of the summer. It was brilliant fun.
Let's now talk about good conductors of electricity. And we're talking about metals. Gold, silver, copper, very, very good conductors. Copper, now this is how it works. Copper has 29 positive charges in its nucleus and 29 electrons going around it, which makes it neutral. But even at room temperature, the amount of vibration of those atoms can chuck off an electron. We call it a free electron. And so that leaves this copper as -1 electron, which is the same as being +1 charge. It's positively charged. We call it an ion. You've heard the word ion, a positive ion and an electron. But if it's positive, it's attractive to other electrons, and so on and so on and so on. So these free electrons are moving around randomly all over the place. I'll show you a picture.
These free electrons are very easy to knock off, and so just by rubbing, for example, like with the amber, you can actually knock an electron off an atom.
One atom came along and saw its friend, another atom, just looking very, very sad. So he said, "What's the matter, little atom?" And the other atom said, "I've lost an electron." And the other one said, "Oh, are you sure?" He said, "Yes, I'm positive."
Back to our free electron picture. If we make one end of this wire positive and the other end negative, then there's a force on every single electron, and they start working their way up towards the positive end. That is a current.
Let's go back to the link between current electricity and static electricity. Static means not moving. You charge something up, it's charged up. And it's not until you touch it and get a shock that you've got moving or current electricity. So when you charge it up, you're knocking electrons off one of the surfaces and putting them onto the other. So one's charged up positively, one's charged negatively. And between them, there is a voltage difference. Come to that in a minute. Be patient. Okay, if you've got a voltage difference, it can actually cause a spark, which is making a current, as in lightning. In a cloud, the particles and the bits of hail and stuff go up, bash into each other, charge up. The cloud can get very, very charged up. And when the voltage is big enough compared to the Earth, lightning.
That's what happens. The cloud gets charged up in different places, and so current can flow from plus to minus. And of course, if we have that wonderful machine, the Van de Graaff machine, you can charge up pupils in your classroom. There's another very good way to show the link between static electricity and current electricity. First of all, you stroke a cat very hard for a few seconds and then touch its nose.
That picture of the girl with her hair standing on end was great because that's called a Van de Graaff machine, or if you're Dutch, Van de Graaff. And the kids love that in the class, and so do I. My favourite trick on it, you have to stand on an insulated little table, got some polystyrene or something, so you charge up with the big ball on top of the machine. And so I used to charge myself up. Someone would turn a Bunsen burner on with the gas, and I would light it by just putting my finger near the top, and a spark would jump and it would light the gas. They loved that. I did too. It's good fun. Right, now voltage is the thing that makes a current flow. Current's what we want. Current does all the good stuff in electronics, or it makes light bulbs glow and stuff like that. So we want current, but voltage is needed to make a current, and voltage is applied across things. Current flows through them. So when you see a newspaper article that says, poor man died because 100,000 volts went through him, volts don't go through. They're applied across. So we had 100,000 volts applied between whatever bit was touching the positive wire and earth. So it will make a current go through him. You can see birds sitting on high voltage wires. You saw the girl with her hair standing up on the Van de Graaff machine. You don't have any electric shock if you're just attached to one terminal, which is effectively what that high voltage wire is. It's only if you've got a complete circuit that current can flow through to earth. Okay? We've got various ways of making currents and supplying a voltage, because voltage is the oomph. You all know what that's called? Oh, a torch battery, I hear you cry with one accord. No, it's actually a cell. It's a single unit. It's got carbon rod in the middle, it's got a zinc casing and mushy ammonium chloride inside, and that gives a voltage difference between the top and bottom because there's two different materials. So it's a cell, 1.5 volts. An AA, exactly the same. Same stuff, it's just that there's more stuff in that one than that one. So they're both 1.5 volts, as is an AAA. This can do everything that one can do, except it wouldn't do it for so long because it hasn't got as much stuff in it. This is a battery, and if you look at it, it says 9 volts. And what it is 6 rectangular cells on top of each other inside there, and each cell is 1.5 volts, 6 1.5s is 9 volts. So there's a 9 volt battery. So if we've got a voltage, we can have a current.
Here is my little setup. I've got my meter, which is showing about 0 at the moment, but that's not millivolts, so those numbers, don't worry about those, they're very tiny. You take a lemon, don't tell Pam I nicked it from outside, and 2 different bits of metal. This one's iron and this one's copper. They've got to be different. So we'll put the copper in one end of the lemon, which can conduct electricity, stick the iron nail in the other, and watch what happens when we connect up. Whoa, it's gone right up to about 400 millivolts. That's nearly half a volt. So that is a basic cell. If you did about 12 of those in a row, you might be able to light a light bulb. How about that? I want you to get the idea of voltage. Now think of voltage as oomph to drive the current around the circuit, or better still, electrical pressure. And here's an analogy. Imagine we've got 2 people holding a hose that's full of water. Basically, if it's horizontal, the water doesn't fall out. But if we lift one end, then the water flows out because of the pressure difference, voltage difference, okay? And the water flowing is a current of water. If we lift it higher, bigger voltage, then the water flows out faster, bigger current. So it's a very good analogy between the two. You have a pressure difference, a voltage difference, and it makes a current of water flow a current of electricity flow.
Now, the current is what we want. It can do several things for us. It can work the electronics. It can work heaters, or it can heat things, as in an ordinary electric heater or a light bulb. Oh, by the way, it's quite funny. When you see an advert for electric heaters, it says incredibly efficient. Of course it is, because the only wastage of anything electrical goes into heat. So if you've got an electric heater, everything's going into heat anyway. So it's actually 100% efficient. We can get a magnetic effect, which is very useful to us. And in the early days, it was discovered by someone called Ørsted in the 1800s, and he discovered it by putting a piece of wire, which was carrying a current, near to a compass. I'll show you.
Okay. Here's my apparatus, a cell, a piece of copper wire, and a compass. Look, see, the compass always points the same direction. Actually, this was my old compass and thing from when I was at school in the 60s. Look, it's got magnifying glass on one end, and one of those things that you run up and down a map to get the distance gone. Anyway, let's go back to the compass. Now, there's the compass. And what I'm going to do is get the copper wire, slightly out of the picture maybe, sorry about that, and hold one end on the battery, the cell, whoops, and watch what happens when I make the connection on the other end of the cell. Watch. Do you see the needle go? The needle on the compass deflects, off it goes to the right. So that's the current flowing through the wires giving a magnetic field. Now, if I turn the battery around the other way, I think what you'd all expect to happen is exactly that. The magnetic needle deflects in the opposite direction.
So one of the useful magnetic effects is, of course, an electromagnet, but it's used here in this demonstration in an electric bell. So here's how an electric bell works.
This is how the electric bell works. We have a piece of iron here and a piece of iron here joined together with another piece of iron, and the coil of wire is wrapped around them both so that this becomes an electromagnet. So if the current flows through that wire, then this becomes magnetized. So let's have a look and see what happens when we push the switch. Push the switch, you close the circuit. By the way, as a matter of interest, we never say we turn a switch on or off. We open or close a switch. It's the circuit that turns on or off. So we close the switch, turn the circuit on, and the battery delivers current. And the current can flow through here, round the coil, out the other side, and back again. Therefore, this becomes a magnet. But look, this is iron, and so iron is attracted to magnets, and so this piece comes over here, gets attracted to the magnet, and that goes boing as it hits the gong. But once it's there, because this is springy, it breaks the circuit because that bit gets pulled away from the contact. It's not actually a physical contact there, it gets pulled away. And so once it goes over, it breaks the circuit, which means the magnet turns off, so the spring brings it back again. And so therefore, all the time the switch is closed, this is going dong, 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 dong. That's slow motion. If you want it fast motion,
Yeah, that was how an electric bell worked. Now, AC or DC? I am not asking you your sexual preference. I'm just talking about alternating current and direct current. In direct current, the current always goes in one direction. It goes from the positive terminal through the circuit to the negative terminal. So we've always got all the electrons are flowing in one direction. AC means alternating current. And if you could see the free electrons in the piece of wire, each electron would be going backwards and forwards because the voltage goes one way, then the other, then one way, then the other. And the best way to show it to you, and I know you don't like graphs, but is on a graph.
So are you ready for this graph? By the way, look, I'm economising. That picture's on the other side. But you didn't know that, did you? Right. The generator in the power station is generating a voltage which is alternating, and that means that we've got positive volts and negative volts. Remember, that's just direction, so we'll call 0 in the middle. It means that the voltage goes up to a maximum and then down to 0. And then it does exactly the same in the opposite direction and back to 0. So that's what a graph of voltage against time looks like. It increases to a maximum, goes back, and then although this looks like it's underneath, it's just increasing to a maximum and back again, but the other way round. And the time interval of this happening here is 1/50th of a second. That's because the generator rotates 50 times a second by law, and they call that the frequency of the mains 50 Hertz. Don't confuse that with the voltage of the mains. 50 Hertz is what we have, and by the way, in America they have 60, but it doesn't matter. Now, we've got 230 volts, but the funny thing is that if you look at this, it goes up to a maximum positive, up to a maximum negative. The average of that is 0. So we've got to have some sort of average, which is 230 volts, although it is changing all the time, as you've just seen. That does actually mean that it peaks at about 320 volts, which is all right, but it does mean that between the top and the bottom, you've got about 640 volts. So there's quite a big difference between the two.
Now, as it happens, we've got to use AC to distribute electricity around the country, because if we use DC, and I'll tell you why this is so later, if we use DC, you'd just lose all the energy before it got very far. So we need AC. So we use in our country 230 volts. Other countries use different ones. America uses 110. Doesn't matter, it still works. So we use 230 volts. And what happens then is we could have our two terminals that are doing the oomph, and they could be, in terms of voltage, doing this. But that makes it a little bit unsafe. So what they do is they say, well, instead of two voltages varying on the two pins, we'll keep one fixed at 0 volts. We'll call that the neutral. And the other one has got a lot of oomph in it. It goes a double amount of voltage. And so that one we call live. And that's the one you don't want your fingers to touch, because if you do, you'll get a very nasty shock. Okay? So that's how the live and the neutral works. We won't deal with the earth pin in this superb lecture. Therefore, switches and fuses must go on the live side of the circuit. And I'll do a little diagram to show you why you want it to be on the live side of the circuit.
Now this represents a wrongly wired socket. This is a socket that you'd put a light bulb in. So you've just taken the light bulb out because it's broken and it's wrongly wired. So let's see what happens, because that's the live and that's the neutral. And these are the two prongs inside the socket. So along comes little Jimmy, because you've gone off to find another light bulb, can't find it. And little Jimmy comes along and says, oh, what's this? Of course, the point is that this is live, whereas this is nothing anyway. If it was that way round, and here was the break in the circuit with the switch, then that is no longer connected to the live, no matter whether there's anything plugged in or not. So that's the safety point, and the same applies with fuses.
Now, the best thing about AC is the fact that we can use transformers with AC. Now, transformer is a clever device, very, very simple, which can change the voltage. Now, in your main socket, you've got 230 volts on average, but your electronics in your computer only wants 12 volts or 15 volts maybe. So this is from my old laptop. You've got one of those, and that's a transformer. In, you're applying 230 volts, and out, you're applying 12 volts. So it just can change it. You can also make it bigger if you want it to, and we'll come to that in just a moment. There's actually a little bit more to it in there, because electronics wants DC, but this is AC. So there's something else in there called a rectifier, and a rectifier changes AC into DC. So in goes 230 volts AC, out comes 12 volts DC. That's rather good. And the other reason that we need transformers is for the transmission of electricity, to make it as efficient as possible.
A transformer is a very clever little device. It's very simple, but it's very effective. Now what happens is you've got a voltage applied here, and this represents the alternating voltage that we looked at before. So let's supposing this is the main voltage and this is 230 volts, for example. 230 volts. Well, we've got a coil of wire here, and a coil of wire with a voltage makes an electromagnet. And what happens is this core here is iron, so it becomes magnetized. But hang on a minute. Here, the magnetization direction is changing 50 times a second. That means the magnetic field in here is changing 50 times a second. And interestingly enough, to make a voltage, you need a changing magnetic field. So if you've got a coil of wire over here, that coil of wire is sitting in a changing magnetic field. It likes that, and it gets a changing voltage set up. If that's 50 hertz, which we know it is, then this must also be varying at the same amount. And so therefore you can make a current go in the second circuit. So there's no electrical contact through here, it's a magnetic contact. That's completely different from this, and we call it the primary coil and the secondary coil. Now here's the magic. If, for example, we had 1,000 turns on that coil and we had 100 turns on that coil, then that's only picking up a tenth of what that's putting out. So the voltage there is not 230 volts, it's 23. If it had only 10 turns, it would be 2.3 volts. And so that's how we have a step-down transformer. It's just all to do with the number of turns. And the voltage output to the voltage input is in the same ratio as the number of turns on the second coil to the number of turns on the first. So it's very easy to work it out. You've got 230 volts in. If you want this to be 15 volts or whatever it is for your electronics, then you just get the numbers right. A transformer. Of course, if we put it the other way around, if we had 1,000 turns here and we had 2,000 turns there, then we get twice as many volts out as we would in. It's not magic, because if you get more volts, you get less current.
Now, I know you don't like equations, but I'm going to give you one, and then we're going to look at a picture of how electricity is just distributed across the country and talk you through why we need transformers.
Here's the equation you've been waiting for. Power equals voltage times current. Now, power is measured in watts. It's actually energy per second. So power is measured in watts. Typical example, an electric kettle, 2.5 kilowatts, 2,500 watts. The old type of light bulb, 100 watts. So power measured in watts, voltage is measured in volts, and current is measured in amps. So for a certain power, you could have a big voltage and a small current, or you could have a small voltage and a big current. Bear that in mind. Here's the real reason we use alternating current, because we've got transformers. So the power station produces something like 12 kilovolts, that's 12,000 volts. You don't want that in your house. And we have a step-up transformer, that means it increases the voltage, and it steps it up to 400,000 volts for the big wires that go across the country. Now that means, if you remember from before, big voltage, small current, and since it's current that heats things up, it means there's not much heat in those wires, so not much wasted. Right, when you get near to a town, you have a great big step-down transformer. Now, we got one of those at Hartley. That's a big transformer station for all sorts of things. And that transforms it down to a certain voltage. It depends on where you are. Around us, we have another one in here, another step-down transformer, and that's outside the co-op. You can tell it, if you walk near it, you can hear it humming. Do you know why a transformer hums? Well, it's because it doesn't know the words. I'll tell you later the real reason. And then you have another step-down transformer in a local area that serves quite a few houses. And you've probably seen these. You see a fenced-off thing that says, "Danger, electricity, keep out." And there's a big green box inside. And sometimes if there's a power cut, it's that's failed. And you see that all the houses on your side of the road have gone out of lights and the other side haven't, or something like that.
So step down transformer. So we stepped it down to, well, 230 we use now for the house, and that's how it all works. The national grid. This is how the power station actually produces electrical energy. There it is going off. We've seen that before for the national grid. Basically, it's a generator, which is a bit like an electric motor the wrong way round. And the same sort of thing where you can buy portable generators, but this is a great big one. As we said before, made to rotate 50 times a second. It's made to rotate by a whole load of turbines joined onto the shaft, and the turbines are rotated by incredibly high pressure steam. You can get incredibly high pressure if the whole thing is a sealed unit, which it is, and you actually boil water into steam and it becomes superheated. It's much hotter than 100 degrees, but it's got loads and loads of energy, so it can give that energy to these turbines, which turn the generator. Then after that, the hot steam is cooled and condensed and goes back into water again. And sometimes that's often what you see in the cooling towers when you see a power station that looks like this, and there's water dripping out the bottom. They're cooling towers to cool the steam. And what annoys me sometimes, actually often on telly, is when they talk about pollution. They say, oh, there's stuff coming off like this. And they focus up on it when they talk about pollution. But that's just steam. That's water. That's not pollution. Anyway, so there we are. That's how it all works. But you've got to heat the water. And you've got various options. You can have either gas or oil or coal being burnt, and that gives heat to boil the water. Or, and this is the only difference from a nuclear power station, you use nuclear energy from nuclear fission, it's called. It's just like a very slowed down atom bomb, but it can't go bang. So you use the energy that comes out from uranium and plutonium, which gives out a lot of heat, and that then heats the water indirectly to do the same thing. So all that lot is the same, whether it's a nuclear power station or a non-nuclear power station. And that's how they work. There, so you've learnt all about volts and amps and watts, hopefully. You know about AC and DC. You know how power is generated and how it's transmitted across the country. There's not really a lot else to tell you on that. So that is about all I've got for you. So thank you for listening if you have been. And my coffee's cold.